All right. So, welcome to week 12, most of the way there. Armadale's enjoyed some freedoms this weekend, but I'm not sure everyone else is getting that. And it also means that most things on campus haven't changed. Um, my impression is there'll be no more face to face teaching for the rest of trimester, and there won't be any component of the field trip as part of this course or as a virtual field trip, as the semester has gotten away from us. So we just progress with the finalising those assessments and completion of the exam, and we're done. Happy days. So today, we're talking about hydrothermal mineralising environments that are related to metamorphic fluids predominantly. So we can look at orogenic gold deposits. We can think about things like cobalt style, so they're more of a base metal orogenic deposit, where there's a contribution from sedimentary settings, and kaolin style deposits, which are mainly distinct from orogenic gold by being associated with extensional tectonics. So orogenic gold, so they're one of the main and richest sources of extractable gold on the planet. There's many systems. They're dominated by gold only, but you do get cases where you have things like antimony. Hillgrove to the east of Armadale is classic for an antimony gold system. They predominantly occur in convergent margins because we have to have that compressional events to induce metamorphism. So we also need a bit of high heat flow. So back arc basins and fore arc basins are quite prominent regions for orogenic gold deposits. The ultimate source of the hydrothermal fluids is partially controversial, but most of it is dominated by metamorphic fluids. As we dehydrate metamorphic rocks, the fluid is liberated from hydrous minerals and is moved up into the system, where it deposits out gold amongst other metals. But we do get an evidence for mixing with potentially magmatic or meteoric fluid as well. So yeah, that's the main source. So this is a idolized crustal section here. We have subduction zone, oceanic crust entering the mantle. We have the main continental material, and in this case we have an accretionary wedge, which is hydrated sediments, predominantly sort of volcanic derived sandstones and shales. And we bury them, deform them. We increase the temperature, predominantly in a sort of across green schist to amphibolite grade conditions. And we dehydrate the metamorphic minerals. They release water. They move up along structurally controlled systems, and we can deposit gold out through those fluids. So this is a sort of generalized example of orogenic gold, but the main idea is that it occurs where we have prograde metamorphism and associated with mountain building, so compressional tectonics. We might get them in other components of this system, maybe in the back arc or even in the main portion of the arc, where we have high heat flow and metamorphic reactions releasing fluid. So how this works: when we increase temperature, predominantly, less so with pressure, the clays progressively become unstable. They're replaced by hydrous minerals such as micas, chloride, and then eventually by anhydrous minerals such as feldspar and garnet at much higher grades. But the breakdown for orogenic systems is mostly related to micas and chloride at the green schist amphibolite facies transition. So we release predominantly hydroxyl components that form water, but we can also have things like methane and CO2, so carbon from the organic matter, especially in accretionary systems that are released in that fluid and mix with water. We also get hydrogen sulfide from marine sediments, sulfate from the seawater. Predominantly the fluids in these metamorphic systems are of low salinity, because the pore water is removed. We're mainly worried about water that's coming from hydrous minerals, and along with chloride and other complexing anions is the main nature of this fluid. So it's fairly reduced, low salinity, and most of the complexing occurs with hydrogen sulfides. So orogenic gold, we then have to liberate that fluid. It moves along prominent conduits, mainly shear zones or fault zones, and then gets to higher levels where it might form veins. So we have to heat it, metamorphose the sedimentary sequence, and it might interact with meteoric waters. So then the gold, as it moves through this fluid, precipitates in different deposits related to different processes. It might be pressure or boiling in the very shallow crustal component. It might be mixing with maybe meteoric water, or we have an immiscibility, so we have phase separation in the fluid, in which case it might mean that gold is no longer stable in the fluid. Could be reaction with wall rocks as we alter. We have fluid rock interaction, and that changes the dynamics of the fluid, releasing out gold. Or it just could be just a decreasing temperature where we reach saturation points for CO2 and hydrogen sulfide. So most of the mineralization occurs in veins, but it can be partially disseminated. And the width of alteration depends on the permeability of the host rock. So that can be depth and rock type. So yes, so metal complexes become unstable and the metal precipitates out as this usual story with metal sulfides or other minerals, quartz, scheelite, but we might get pyrite in these systems as well. So here's just a schematic representation of broadly what orogenic gold systems are. We have deep level sediments here being regionally in contact metamorphosed. We might have some fluid coming off the intrusion, but we react out. Predominantly the gold resides in metamorphic minerals like ilmenite, and they break down with hydrous phases like chlorite at the green schist amphibolite transition. The water is released and it carries with it gold. It might move up through prominent conduits like faults or shear zones, move higher into the system to around temperatures 200 to 350 degrees, where we have a change potentially by boiling or interaction, and it precipitates out as a native gold, potentially in pyrite or in arsenopyrite or stibnite, as we decrease the temperature. So most of these deposits occur at the brittle ductile transition, and so they're at quite shallow or broadly medium depth mesothermal systems. So as there's limited chloride in this fluid, you cannot transport elements such as iron, copper, and the base metals. It can, however, transport metals that complex with HS, such as gold, stibnite, arsenic, maybe silver, beryllium, tungsten. So that's why these orogenic systems are dominated by these elements. In Hillgrove we have gold, stibnite with some arsenic, and in places tungsten as scheelite, but many are just predominated by gold. So this is how these systems work. They predominantly could be distal from their actual source. So here's some classic examples. In the Yilgarn Craton around Kalgoorlie, the Golden Mile is a classic example of orogenic gold. They're quite common in Archean terrains where we have greenstone belts. We have mafic rock metamorphosed at the right conditions and transporting material up. And this is just an example of a crustal model of orogenic gold. So as we go to deeper levels, we increase the rate of metamorphism from green schist, amphibolite to granulite, so increasing in temperature. We might have granites in the depth, and they contribute to moving in metals like lead, strontium, and gold. And we also have metamorphic release of lead, strontium, and gold, moves into these conduits, progresses up through structural shear zones, faults, moves up towards the brittle ductile transition, where we start to develop orogenic gold systems. And they're mostly at this level, but we might get even shallower interaction potentially with seawater or meteoric water. And here's some examples of some of these gold deposits and their conditions. So the Golden Mile in this classic brittle ductile upper green schist facies conditions. And this is, variation on the theme again. So here's the mega scale process in a subduction zone where we have orogenic mountain building process going on. Here's the mesoscale that I just discussed along a prominent structural control. And at the ore deposit scale, we might have phase separation to cause deposition. So we might have prominent water, sodium chloride fluid inclusions, or we might have a fluid rock interaction where the fluid interacts and alters the surroundings, and that leads to the breakdown of those metal complexes. So the styles of alteration in these systems are mainly carbonate, silica, sericite. The carbonate is typically reduced as an iron-bearing carbonate like anchorite or siderite, and this tends to replace the feldspars. In higher deposits, calcite is the dominant carbonate. We have a range in temperature and styles from shallow, so subgreen schist, up to high temperature granulite facies, but it's always associated with metamorphic rocks and processes. The gold occurs as free or as a competent dissolved in sulfides such as pyrite or arsenopyrite. So at times it can be very difficult to extract gold in these deposits, particularly if it's occurring in things like stibnite. The common metal infantry includes arsenic, potentially bismuth and tungsten, and there is a strong structural control on these systems because the fluid is moving through prominent conduits. Could be shear zones of faults, you might have breccias, or along geological boundaries, because it's related to that fluid, its movement, and where that fluid changes its dynamics to precipitate out metals. So low temperature deposits will have brittle features like brecciation and craxial veins because they're up at shallow conditions. Higher temperature ones will be dominated by ductile features, shear zones and myelinites. So hydrothermal minerals, as always, reflect these variability in conditions as well as fugacity, but most deposits are low sulfide dominated by pyrite or pyrrhotite at high temperature with arsenopyrite. And we have low base metal values because the fluids are not saline and there's no chloride complexes to carry things like copper. So that's why they're dominated by gold, arsenic, antimony. They're predominantly related to metamorphism, as the name suggests, so they're syn or post-peak, and they're commonly deformed, but not necessarily. And they most chemically react with, so most chemically reactive rocks form the best hosts, or where the fluid interacts and deposits out. So mafic rocks, politic sediments, and less commonly felsic rocks. So here's a nice example. This is visible gold here in an example of a high temperature. So it's 500 to 600 degree ore zone in a myelinite from the Plutonic gold mine in Western Australia. We see prominent metamorphic fabric here of the myelinite. We have abundant veining, and some of the veins that are carrying gold have actually collapsed around where the visible gold is present. Here's a slightly different example. We have the carbonated alteration around the intrusive rock here, this prominent brown alteration, which is common for orogenic systems. And here it just shows you this structural control. We have these prominent dark graphite fault zones, and that's where most of the actual metal deposition is occurring, because this is where the fluid flow is focused. So we have abundant examples all throughout the world. As you can see here in Australia, particularly Kalgoorlie, we also have the Bendigo Ballarat area. We also have things like Hillgrove and Gympie in Queensland, and New Zealand. They have things in the Otago schist, but there is quite a common association to Archean greenstone belts. So that's all I'm going to talk about orogenic golds. I'm going to move slightly on to a distinct style called Cobar style, or base metal orogenic systems. And so Cobar is a type example. So in western New South Wales, around the township of Cobar, they're mainly, well, the deposits are situated in an ancient sedimentary basin called the Cobar Basin. So they're unique, but also controversial in terms of their deposit formation and metallogenesis. They form in a metamorphic terrain associated with orogenesis, but they have high base metal concentration, which is distinct from the low salinity reduced fluids typical of orogenic gold, because they need chlorine complexes to carry some of these base metals. So the features that are common is that the fluids are structurally controlled and have similar metal inventories, but they have higher base metal content, particularly copper. So we get massive sulfide lenses with exhalative host rocks and similar deposition morphologies to VMH deposits. So these rocks are mostly in turbidites. So we have a slightly distinct style and metal association. So here's some of the classic major deposits in the East Cobar Basin. We have a variety here. We have Endeavour, lead, zinc, silver, CSA, copper, lead, Great Copper, Great Cobar and New Cobar and Peak, all copper gold with some base metals. So you have quite a distinct style that might be hosted in turbidites or in fault-bounded material. So there's a range of styles and nature of these deposits, and here's just an idea of their actual metal content. This is reasonably old data, but high copper, lead, silver values, and variability in the base metals. So we get prominent hydrothermal alteration of the host, dominated by chlorite, cerussite, and quartz, similar to orogenic gold. Many, but not all, quartz vein hosted, but we get stringer and replacement style mineralization. The host rocks are lower green schists, and this is where the controversy starts: is what are the hydrothermal fluids? They can include they're likely to include basinal fluids from a sedimentary environment and metamorphic fluids. They must be saline to carry the base metals, and the mineralization is syn deformational in many deposits. So in this case, we have a combination of metamorphic fluids and basinal fluids from the sedimentary basin combining to carry base metals, and a lot of the base metals would come from the basinal fluids, and the metamorphic fluids carry things like gold, and they've mixed to produce a saline system that has chloride complexes to enable metal transportation. Here's just some examples of massive sulfides in some of the ore at CSA. Here we have the Marley Bull. We have replacement textures, evidence of deformation. We have prominent fabrics in here stringing out of the sulfides. We have structural control along fractures and veins. So quite a distinct style. Some more examples here, some sphaerolite and galena precipitating in favourable sites around clasts. We have sphaerolite and galena here forming around some of these deformed sedimentary structures. Okay, finally, and reasonably briefly, kaolin trends. So these are a similar style to orogenic gold, but they involve extension. So instead of compressional tectonics to cause metamorphism. We have an extensional system that enables the fluids, some heating and the fluids to move along extensional structures and pond in prominent sedimentary basins. They're mainly related to deposits in Nevada. They can contain high gold contents associated with Paleozoic sediments undergoing faulting and extension. So the host rocks are sedimentary, carbonates, siliclastics, and coarse clastic sequences. And the intrusive rocks include dike sills. And so the mineralization formed between 42 and 36 million years, and the product of continental passive margin tectonics and subsequent compression. So we have this extension, enables fluids to move, and then we compress them up and enable uplift. So there is more complicated fluid story here. We're getting a combination of potential metamorphic and basinal systems, and they're hosted by Paleozoic sediments. So here's just an example of a deposit style. So it's epigenetic. The fluid is a combination of meteoric, metamorphic, potentially with some magmatic, dominated by gold, silver, arsenic, stibnites, very similar orogenic systems, except we're not mainly associated with compression. Lower temperatures, 180 to 240, low pH, low salinity. So that's why the metal association is very similar to orogenic gold. And hydrothermal alteration characterized carbonate, silicification, and argillic. And gold occurs as ions with sulfide minerals, and there's tiny inclusions in pyrite, arsenopyrite, marcasite. So we have these extensional structures that act as conduits, potentially coming through these fluid systems, and they pool into an area where we potentially reacted with different boundary rocks, maybe a carbonate, particularly reactive, versus a distinct shale, and therefore the metal is deposited out. So we have these structural controls that will enable the gold mineralization, and then we can actually then thrust the system up during compression to change the structural form, create traps. So this is why there's a prominent association with the fold and thrust belts of the basin and range tectonics in America. So we have periods of compression to squeeze all the rocks together, and then they extend out and form these extensional structures and grabens that can drive this kaolin style gold deposit. So that's all from me for today, and I'll catch you later.